For years, the world of AI was dominated by recurrent and convolutional neural networks, systems that processed information like a slow assembly line. But in 2017, traditional models like LSTMs processed data one word at a time. This sequential nature created a massive bottleneck, making it impossible to process huge datasets in parallel and causing the model to forget distant connections. Enter the transformer. It proposed a radical idea: ditch recurrence and convolution entirely. Instead, rely solely on an attention mechanism to draw global dependencies between input and output. The architecture is split into two parts: an encoder that understands the input and a decoder that generates the output. Each layer uses self-attention to look at every other word in the sequence simultaneously. Think of self-attention as a search system. Each word has a query, a key, and a value. The model compares the query to all keys to decide which values are most important. This is scaled dot product attention. But one perspective isn't enough. Multi-head attention allows the model to attend to different parts of the sentence at once, capturing syntax, grammar, and context through multiple heads in parallel. Because there's no sequence, the model needs to know the order of words. Positional encodings act like timestamps, injecting unique sine and cosine waves into the embeddings to give the model a sense of time and place. The results were groundbreaking. The transformer achieved state-of-the-art translation scores while being significantly faster to train. It achieved 28.4 BLEU on English to German, outperforming even the best ensembles of the time. Today, this single paper is the foundation for almost every modern AI, from GPT and BERT to the generative revolution we see today. It didn't just improve translation, it redefined the limits of machine intelligence.